We're going to turn our attention to an important application of statistics here, where we're going to be talking about both modeling and making predictions for bivariate data. So data or information that comes from considering two variables. So, a very practical example of something like this might be using a machine called a spot welder. So what a welder does is it essentially melts a little piece of metal to stick together two other pieces of metal. So a spot welder puts a little circular spot, and you might be interested in the strength of that spot, that weld, versus a function of its diameter. So in this case, what you would want to say is that one of the variables, so the diameter of the weld, would be the thing that predicts or creates a response in that output variable. And the output variable here would be the shear strength of that weld. And so this is the type of scenario we're going to be in. We're going to have one variable hopefully causing a response in the other one. Now, ultimately, the goal is to figure out cause and effect. Does one variable cause something else to happen? But before that, we're going to be content with trying to make predictions about one versus the other. So when we've got bivariate data, we've effectively got two variables here. And from that, we're going to make a series of a whole bunch of observations. So we're going to have n of them. And because they are observed values, they're actual data values, we're going to use lowercase letters. So x1, y1 is considered to be a pair. And then that pair is going to go all the way through all of our observed data values. Now, if we have bivariate data like this, what we want to do is analyze. And the easiest thing to do is to come up with a visual. And that visual is something called a scatter plot. Now, when you have a scatter plot, imagine each pair of data values is kind of like a little stone or a marble, and you got a whole pile of them in your hand, and you're going to scatter them. You're just going to throw them about on the ground and see where they lie. So if you think of one axis being x, the explanatory, the other one being the response, all of your data points are going to scatter around kind of like marbles on a ground or on a page, and they make some pattern. Now, that's an easy first step. Now, software like R or a graphing calculator can easily come up with these scatter plots. We typically don't do this by hand, but for the purpose of just explaining here, I'll draw one by hand. Now, what we want to do here, we want to come up with a model that we can eventually make some predictions, right? What we're trying to do is predict. Can I predict y values based on this x data? Now, to make predictions, I then need a model. The simplest model that we can come up with here is a linear model. And what we're going to be interested in is whether or not the x values are linearly related to the y values. Are they linear related? And the linear relationship that we're going to try to assume here is just given by these terms. Now, this thing b naught is going to be the intercept parameter, and it's kind of like the y-intercept in a regular linear equation, and then b1 is going to be what we call the slope parameter, right? And these are things that we don't know. And the idea is can we figure out some line that goes through this data? And then another question is, what line, we'll say, best fits this data? And then how do we find it? And ultimately, the thing that we're going to have to determine is these values of beta naught and beta 1. Now, to do this, we need an idea. Best is kind of vague, so we need to define what we're saying by best. Now, there's lots of different ways to define best, but one way that we're going to try to talk about is with this concept of a line in modeling and data points. So if I give you my line here, I'm going to have a data point. Now, the line that I choose may or may not actually go through that data point. And so this is our observed value. So if you tell me an xi, this yi is what I get. Now, if I'm using a line to make a model of it, for the same value of xi, I might get a different value of yi. And then I'm going to put this little hat on it. And this is what I would call the predicted value of my data point. Now, there's a difference here. There's a difference, and I'm going to call this thing di, and it's the deviation of the observed point from the line, or the prediction. Now, ultimately, what we would like to do is we would try to make these deviations small, right? So in terms of a mathematical formula, we're just taking the difference between this observed value and this predicted value. So it would be yi. The predicted value comes from our line, b naught plus b beta 1 xi. And these are the deviations for each individual point. We want to try to minimize these. That's, a pretty sensible idea. When we talk about the line that best goes through the data, it kind of makes sense that we would like to get the line through as many of the points as we can. Now, without getting into the details, for many mathematical reasons, we aren't going to talk about minimizing the deviations or even the sum of them. So we don't minimize the sum of the deviations. Instead, we're going to talk about minimizing the square of the deviations. So we're going to minimize the square, or the sum of the square of the deviations. One simple reason is that you could use things like orthogonality from linear algebra, if you know what that means. And regardless of whether we get those terms or not, this is the quantity that we're going to try to minimize. So it's going to be the sum of all of these deviations from the observed values, or the predicted values. To do this, there's a tried and true way. You can use calculus. And in particular, we don't know what this beta naught and the beta 1 are, so that means we've got to go ahead and use multivariable calculus to minimize it. Now, you may not know what that means, and that's fine, but if you understand what a derivative is, all we need to do is we need to find the partial derivative of this sum with respect to each of these parameters. So we need to find those partial derivatives and find them and set them equal to 0 and solve for beta naught and beta 1. So we end up getting a system of equations. The system may or may not be linear. It really just depends on what we end up with. Now, because multivariable calculus isn't a prerequisite for this course, and because the details are kind of worked out in your textbook, I'm just going to skip going through them, and I'll present the final results here for you. But basically, if we've got these deviations, we're going to try to minimize the square of them. So this quantity q, calculus tells us how to do it. We've got to compute these partial derivatives, set them equal to 0, and solve the system for beta naught and beta 1. And then this leads to some big, giant, ugly formulas. Now, beta 1 has an ugly formula, and it's going to be in terms of a handful of quantities. We get n, sigma xi yi. So this is the sum of all the xi times yi. And it's going to be in terms of a bunch of summations here. Now remember that everything is in terms of the data values that we are getting from our observations. Remember, we are modeling data. So this is what you'd get for beta 1. Now, because it's in terms of observed values, we put hats on it. So it's not really beta 1 that we're finding. We're finding a prediction for beta 1 based on observed values. And that's why there are hats on things here. So this is all in terms of observed values from the data. Now the same thing happens here. There's a simpler formula for the beta naught. Y bar minus beta 1 hat x bar, where this is the sum of all the y values. It's the average. And this is the average of all the x values. Now, if you sub those back in, you're going to get a big, ugly expression for beta naught. Now, we like to put this simpler one there because it's going to help us talk about some conceptual things in a moment. But basically, the observed value here for beta naught kind of looks like this. Now, no, you won't be expected to memorize this. This will be provided to you on a formula sheet, and you can look it up in your textbook as needed. But the reality is, a lot of this stuff is coded into software. The exercise here was to be able to figure out, could we get these parameters in terms of the data values that we've got? So remember, the line y equals beta naught hat plus beta 1 hat x is the line of best fit through the observed data. So this is the line that's going to air quote best fit your data. Now remember, what we mean by best is it minimizes the sum of the squares of all the deviations. So sometimes this is called a least regression line. Now, all you need, if you wanted to do this kind of the long way by hand, you just need these values. You need the number of data points, the sum of all the x values, the sum of the squares of all the x values, the sum of the y values, the sum of the squares of the y values, and this weird cross sum xi, yi. For fun, by hand. Now again, when I say by hand, you're going to need at the very least a calculator to do all this stuff, but software will do it all for you. A calculator will do it all for you. I've posted an example here to do with the number of people living on farms in America. So I've given you a table of data, and I've also taken that data and I've plotted it in a scatter plot. Now, the scatter plot looks linear, and that's good. The first thing you should be doing when you get this bivariate data, a table of two variable data, is plotting it. Go through and do any of this modeling or prediction if you can't even plot the thing and it doesn't even look linear. All right? So it's very important that you actually sit there and plot the stuff. Now, if you are interested in doing it the long way, we've given 10 data points. Yeah, the sum of all these xi's is just some big ugly value. Now, your graphing calculator can do this, but again, in practice, we aren't ever going to bother with this. In practice, all of this stuff is automated. Nobody in the real world sits there and presses buttons manually to get all of this stuff down. But for illustration's sake, I'll just write them down. And if you feel like going through and calculating this the long way and trying to verify it all, you could do this. So from that data that I've provided to you in the example, you can calculate those beta 1 and beta naught parameters. So beta naught in this particular case would be 1166.93, and beta 1 would be negative 0.5868. So your prediction line, the prediction line always has a hat on it. So the prediction line would be this. So there is a linear equation, and again, on this example sheet, I have drawn in that least squares regression line. I've put it in, and it's pretty good fit. It looks visually, anyways, like that data more or less has some linear pattern. Now, we'll talk a little bit more about why and what to do with all of those little scatter around the line, right? They don't perfectly go through the line, and we don't expect them to perfectly go through the line, but that's okay. Now, we use the model here, the line, to make some predictions. That's the whole point, right? We make models to make predictions. Now, if we were to make predictions in between the data, then that would be a different kind of modeling. So if we were to make predictions within the data set, this would be something called interpolation. So this is when you choose an input value between known data values. So if I were to make a prediction and pick some other value, let's say, it would be nice. So I'm going to rustle up a value here and try to make a prediction. So if I were to, for example, take 1972, right? I could make a prediction about what the value would be. And, you'd calculate this, you'd get some value, and you'd put it in and you'd get some value. Now, generally, interpolation is fairly accurate. So we like interpolation. It's reliable because you are within the data range. And within the data range is pretty safe. Now, you could make a prediction about the future or outside of your data range. Now, if you make a prediction about, let's say, the year 1990, as has been given here, you are going outside of the data range. And this is something called extrapolation. The prefix extra means outside. And when you make an extrapolation, you got to be really careful. And I'll show you why. So if I were to make a prediction about what's going on in the year 1990, I'd just take my model, I'd plug in all of the numbers with the 1990 here, and here's what I'd end up with. I'd end up with negative 780,600, right? Or I should say even before that. Remember, your model is adjusted to millions of people. So when you were to use your model, you'd end up getting this. Negative 0.7806. Or that is negative 780,600 people. So what my model is telling me is that in the year 1990, I should expect there to be negative 780,000 plus people living on farms. That's nonsense. You can't have negative people, a negative number of people living on a farm. That's why it's very dangerous to extrapolate. The model may not hold, right? That's the key lesson here. The model may not hold outside of your data range. So if you are going to use a model, be very careful if you extrapolate things with it. Interpolation is usually fine because the model is within the data's within that model's range, but going outside, funny things could happen. Now, based on this, as I've been asking you here, the rate of decrease is just the slope of the line. And that rate of decrease here is this beta 1 parameter. And in this case, it's negative 0.5868 or negative 586,800,000 people per year. So this least squares regression is very, very simple, easy way of going about things and making some pretty powerful predictions. We want to be able to say something about the accuracy and how reliable it is, and we'll talk about that in the next video.